Alright, boys and girls, let's continue on with these homework questions. Let's go to number 11. It says, based on their positions in the periodic table, list the following ions in order of increasing radius. Now let's go ahead and bring this up here. And we're talking about a potassium +1. I could just write it as plus. Calcium 2+. Aluminum 3+, and silicon 4+. All right. Now, generally speaking, when we're comparing the sizes of ions, we have to remember that a positive ion or a cation forms by losing electrons. So positive ions are always going to be smaller than the atoms they come from because you've lost an outer electron. So the whole thing gets smaller. In this case, we lost one electron. For potassium. Calcium has lost 2 electrons, so that's even smaller, right? Aluminum 3+ has lost 3 electrons, so you're not losing just 1 or 2, you're losing 3 electrons, so you're sort of whittling away at the size of the atom. And silicon, you lost 4 electrons. So generally speaking, these are pretty easy. The one that's lost the most electrons or has the highest positive charge is going to be the smallest, right? Whereas the one in this case that has lost the least amount of electrons is going to be the largest. So the correct ordering here from smallest to largest is exactly the opposite of how it's listed here. So I'm going to say silicon is less than aluminum 3+, which is less than calcium, which is less than potassium 1+. So that's one way you could signify that with greater and lesser symbols. So silicon is the least big, and potassium is the most big in that case. All right. Now, just for sake of completion, what if we weren't doing positive ions but negative ions? All right. Let's say we had, I don't know, say carbon -4, nitrogen -3, or 3-, oxygen 2-, and fluorine 1-. All right. How does fluorine become a -1 or a 1-? By gaining 1 electron. Oxygen becomes a 2- by gaining 2 electrons, and as you're gaining electrons, you're putting more electrons around the outer portion of the atom. You're making it bigger and bigger. Nitrogen 3- would be gaining 3 electrons, and this carbon 4- or -4 is should be 4- is gaining 4 electrons. Right. So in this particular case, would have to say that this -4 or 4- carbon is the biggest, and that the others are lesser, and you put them in order by their charge here. All right, so fluorine is going to be the smallest. It's less than oxygen 2-, which is less than nitrogen 3, which is less than carbon. And so this is smallest to largest. Okay. All right, that was number 11. Let's try number 13. Let's try number 13. All right. Which atom or ion, we can bring this up here. Number 13. Which atom or ion is isoelectronic with bromine with a charge of 1 plus. All right. So bromine 1 plus. All right. The fact that it has a +1 or 1 plus charge means that it has lost an electron. This bromine atom has lost a negative charge, so what remains is a +1 ion. And so this is bromine, which normally, if you look at a periodic table, bromine is atomic number 35. So it's going to be 35 electrons minus 1. That's where we get the +1 charge from. So that would be 34 electrons. All right. So we need to compare that against selenium +2 or 2 plus, selenium just the neutral atom, arsenic with a 1 minus, 2 plus. Krypton, no charge, just the atom. Gallium 3 plus, and chlorine 1 minus. All right. Let's do it like this. How do you become a 2 plus? By lose 2 electrons. Lost none. All right, it has no charge. -1 means it's gained 1 electron. Lost none, or gained none. 3 plus means it's lost 3 electrons. 1 minus means it's gained 1 electron. All right. Now, how many electrons does selenium normally have? Selenium is right here on the periodic table. It's number 34. So it normally has 34, but it's lost 2, so it has 32 electrons. All right. Selenium, as we just said, has 34 electrons. It's lost none. There's no charge on the sign, so it's 34. Okay, arsenic is atomic number 33, but it's gained 1, so that'll be 34. All right. We could see that we found 2 items already that are isoelectronic with this bromine 1 plus, selenium and the arsenic 1 minus. Right. How about krypton? Well, krypton's got 36 electrons. All right. Gallium, to become a +3, it's lost 3. Normally gallium has, where the heck is gallium? It's 31 electrons. So if it's lost 3, that would be 28 electrons. Well, that's not isoelectronic. Chlorine normally has 17, but it's gained 1, so that'll have 18 electrons. All right, so that's it. The answer to number 13, what is isoelectronic with bromine 1 plus? It'd be selenium, that's neutral, that means it's not lost any electrons. And then the arsenic 1 minus ion also has 34 electrons. Okay, so that's number 13. And let's see, how about we go to, which one? Number 17. Which main group atom? Main group meaning the representative elements. Those are the group A's. And by group A's we mean the group A's, or the representative elements, are the first 2 groups, right, which sometimes we call the S block elements, and then the last 6 elements, the last 6 groups, I should say, right? They're labeled 1A, 2A, and then 3A, 4A, 5A, 6A, 7A, and 8A. They're also numbered 1, 2, and then 13, 14, 15, 16, 17, or 18. These are the P blocks, by the way. So the main group elements, or the representative elements, are the group A, the S and P block elements, right? Not the transition metals, not the D block, or certainly not the guys down at the bottom. The F block elements are the inner transition elements. We only want to consider the first 2 and the last 6. Right? Which main group element would be expected to have the lowest second ionization energy. Alright, this is going to take a little bit of thought on our part here. And what might be a good idea is to look back at the reading that I had you do last Thursday. It was a PDF file, and this one was on page 180. If you want to look through that PDF file, just taken out of what's normally our chemistry textbook. But anyway, all right. What we need to recognize here when we look at these successive ionization energies is the electron configurations of these elements. Let's take, as an example, sodium right here. Sodium has 11 electrons. 1s2, 2s2, 2p6, 3s1 is its electron configuration. All right. This electron, this outermost electron, this valence electron, the 3s electron, sodium really doesn't have a problem giving this electron away or having it taken away. And that's really a measure of what ionization energy is. How much energy do I need to put in to sodium to remove this first electron? Right? And the reason that sodium isn't holding on to this electron very tightly is because once you were to get rid of it, what you then have left is the underlying 2s and 2p electrons, 2s2, 2p6. If you count those all together, they represent what is known as an octet of electrons, and an octet is very stable. So this is actually a good position for sodium. This 3s electron that it normally has, if it were to be removed from the sodium atom, you would end up with a sodium ion, Na+1 or 1+ ion. That was, we would call it sodium +1 cation, is very stable, right? Because instead of 11 electrons, it only has 10, but the 10 electrons organize themselves as in this manner: 1s2, 2s2, 2p6, and this outermost energy level, the N=2 level, contains 8 electrons, which we call an octet, and that is very stable. If you take note, though, that as soon as we go ahead and try to remove one more electron from the sodium atom, one of these 2p electrons, the ionization energy for that second electron is huge in comparison. The first electron only requires 496 kilojoules of energy to remove. The second one, this one of these 2p electrons, requires 10 times that amount of energy to try to remove it. And the reason that that second ionization energy is so high is because you're now trying to remove an electron which is part of an octet. That's why the second ionization energy is so large. All right, let's do the same thing with magnesium. All right, magnesium is element number 12, so it has 12 electrons. So that would be 1s2, 2s2, 2p6, and then 3s2. All right. The first ionization energy for magnesium. First ionization energy for magnesium, we look over here, is 738 kilojoules per mole. Right. The second ionization energy is 1450 kilojoules per mole. It's certainly larger, but it's only twice as large, unlike the sodium where we saw the second ionization energy was 10 times, not 2 times, 10 times. Except now, for magnesium, when we look at that third ionization energy, here's where it really takes a huge leap. 7,730 kilojoules per every mole of magnesium atoms. Right? Why is there such a large jump between the second and the third? Well, let's take a look at where these 3 electrons would be coming from. This first electron would be one of these 3 S's. Let me bring this up a bit. Right? This first ionization energy, 738 kilojoules per mole, is going to remove one of these 3s electrons. So you pump in 738 kilojoules, you get rid of that one electron. Now it's a 3s1 situation. Put in 1450 kilojoules a mole, and now you get rid of the 3s electron. Now look what's left. Once you remove that second electron, what's left is an octet. Now in the n equal 2 level, I have the 2s2, 2p6 energy or orbitals that are all filled up. 2 here and 6 here, that's 8 electrons. That's an octet. Now if I want to remove the third electron, that means I have to remove that from this octet. And that's why there's such a huge jump in the ionization energy between the second and the third in the case of magnesium. Now, that takes us to the question number 17. Where is that at? Which main group atom would be expected to have the lowest second ionization energy? All right. Well, the lowest second ionization energy would have to be in much the same way that magnesium's second ionization energy is so much smaller than the third. We would have to look at the same sort of situation going on with all of the group 2A elements. Right? The first ionization energy is not going to be that big. The second's not going to be that big. But the third would be huge. Right? So we're ultimately looking for an element within the second group here. Now, which one of the elements in the second group would happen to have the absolute lowest second ionization energy? Well, if we go back to the trends that we talked about in ionization energy, the ionization energies go up as you go up a group, which means that the lower ionization energies are at the bottom. So the long and short of it is the answer here has to be Ra, radium. Right? The element in the main group for the S or P block elements that has the lowest second ionization energy would have to be radium. I hope that makes sense. And we'll leave it at that. If you would, just finish the other questions on your own and get them into me by, we'll say midnight tonight. I'll put a due date midnight tonight, or midnight Monday night. All right, bye now.